All right. Our next example is no longer about linear algebra. Now it's going to be about probability. So imagine that in one day at KAIST we have two lectures, two special lectures. Oops. Yeah. At the same time. All right. So some students want to go to lecture A, some students want to go to lecture B, but they cannot go at the same time because they are in the same time slot. And KAIST has many student clubs. So let's say C1, C2. These are the list of clubs, student clubs. Right? Now, the question is the following. Can you assign students to one of the two lectures so that in each student club there is at least one student in each lecture hall. Right? Because we don't want to make a situation where some club has no member in one of the lectures. Right? This is to ensure that after the lectures in each club they can share the information about these special lectures. Right? So you have a list of students clubs. So these dots represent the students and circles represent the clubs members. And you can think of it as a set, right? So each student is a member or some number, and you have a set of numbers, a set of students. So when can we assign like the students in such a way that no club completely go to one lecture? And this is the theorem due to Erdős in 1963. He proved the following. If each club has at least k members and number of club is less than 2 to the k minus 1, then it is possible to assign student into one of the two lecture halls so that no student club is completely in one lecture hall. Okay, so as long as each club has at least k members and number of student club is not so big, you can do it. And the condition that each club has at least a certain number of members is natural, because if you have a club with only one member, then no matter how you assign that student to one of the lecture hall, that club will not satisfy this condition. All right, so it's natural to have a lower bound on number of students in each club. And how do we prove it? And it turns out that the proof is not that difficult, just by using randomness. So we randomly assign each student to a lecture hall, to one of the 2 lecture halls with the probability half independently. Right? So for instance, each student has a coin, they toss a coin. If it's head, then it goes to lecture A. If it's tail, he goes to lecture B. Okay? Now, let AI be the event that all members of CI are completely in one lecture hall. Okay? That's the event. Then what is the probability that this AI happens? Well, the probability that AI happens is, well, number of members is, if number of members is CI, I mean K, no, it's not K, it's at least K. If the number of members is L, then it's half to the L. That's the probability that everybody goes to one lecture hall, and another half to the L to the another lecture hall, right? So I have to multiply by 2. And this is less than or equal to 2 times 2 to the minus k, so it's 2 times 1 minus k, 2 to the 1 minus k. So that's the probability that all of the members of CI went to the completely in one lecture. So this is the probability that bad event occurs, right? AI is the bad event. So what is the probability that union of them occurs, or any bad event occurs? Well, it's same. It's the upper bound of that is sum of the events, and this is less. This is equal to k. No, m times 2 to the 1 minus k. And since we assume that m is less than 2 to the k minus 1, so this is less than 1. So what does this mean? So the probability that the bad event occurs is less than 1. So therefore, there is a positive probability. Then none of AI occurs. Okay? So that's the situation where every student club is happy. So that's the proof. So in this proof, we don't necessarily construct such a thing to show this, right? So so in this proof, we just use randomness to construct something, and the proof shows that there exists something, but it doesn't necessarily show how to actually generate one unless you use coins. And there are ways to improve this bound. Okay, this 2 to the k minus 1 is not best possible. If you have time, we can try to discuss it later. Anyway, this is one of the powerful methods. So this is called the union bound, and it's quite common, very often used. Now I want to show you another theorem where you use typical combinatorial method to prove something like this. Now we don't use probability, we don't use linear algebra, we use induction. Okay, suppose that each club has at least one member. And Ci intersection Cj is never equal to, never has exactly one member in common for all I and j. And even if I is equal to j, so maybe I should say it's at least two members, okay, each. Then it is possible to assign students in that way. All right, so now we don't have restriction on number of student clubs. We just have a condition that the intersection of two clubs cannot have a unique member. Either they don't intersect, or if they intersect, they have to have at least two members. How do we do that? And this is by induction, actually. Okay, how do we do that? Right, so let x1, x2, xn be the list of students, right? And we say an assignment of x1 up to some xi is bad if all members, there is a club all of whose members whose members are completely in one lecture hall. Okay, now imagine, so, and I'm using induction, so induction on I. So if I is 1, so the claim is there is an assignment of x1 up to xi that is not bad. That's the claim. I'm going to prove it by induction on I. So if I is 1, I put the x1 arbitrarily, right? Put x1 into an arbitrary lecture hall. At this moment, no student club is bad. No student club is bad because each club has at least 2 members, and the other member is still not, still not in any of the lecture hall, right? So now let's assume I is bigger than 1, and assume, so we can assume that x1, x2 are already assigned to one of the 2 lecture halls, so that no club is bad. All right, now think of the xi. If my xi goes to the first lecture hall, I have 2 choices, or second lecture, right? And if I put xi into the first lecture, and if it's not bad, then I'm happy. So I can assume that if I move xi to first lecture, it is bad. That means we may assume there is a club, let's say CI, in the first lecture. So CI, all members of CIs are in X1 up to X. XI and right, and XI is in CI. And similarly, if I put XI into the second lecture, there's another club whose all the members are in the second hall, right? So there's a CJ. In the second lecture hall, which contains XJ, no XI. Oops, I shouldn't use CI. Okay, so let's change the indices. So it's C and D. And D is also a subset of X1 to XI, right? This is because all the members of D are already they already know where to go. Now that means C intersection D has size exactly 1, contradiction. Right. So that's it. So you can one of these two choices must give place. Right. It's a simple induction. So in this course, you will see some of the proofs using mathematical induction, and this is basic tool for combinatorics. Okay.